So hello, welcome back. So in the last class, as you have seen that we discussed the limit phenomena of homogeneous mixtures, in the sense that we were talking about under what condition given system of a given mixture, a homogeneous mixture, can ignite, then what time it would take to ignite. And first we did the analysis without any heat loss, then we did the analysis with heat loss with different complexities. That is, we considered that the fuel mass fraction changes very little in the initial time, and then we went into incorporate those complexities also, where we were discussing with for a flow reactor, where basically we found this conditions where basically the heat generation balances the heat loss, and which we have shown that one of them will correspond to the ignition and one of those will correspond to the extinction, and we could use this S-curve analysis to basically explain that. So those we did both transient analysis and we did both as well as steady state analysis, and we developed the concepts of ignition essentially, and we discussed the concept of extinction also. But here we will but so far in none of those analyses we considered any flame as such. So as you know by now that the difference between a homogeneous mixture combustion and that between a flame is that a flame not only incorporates reactions, it also incorporates transport. So it incorporates diffusion, and that is what makes a flame different from homogeneous combustion, and where there is no temperature or species gradients. In a flame you have got very strong temperature and species gradients. So those temperature and species gradients add complexity to this kind of extinction analysis, but that is more practical, because in a gas turbine engine or in a scramjet engine what you have is essentially the flames. So to understand whether the flame that we are creating is whether that can survive or not, we need to understand how extinction happens inside a real flame. Once again, as I tell you that of course the combustion that actually happens in a real gas turbine engine, okay, the combustion that happens in a gas turbine engine or in a scramjet engine or in any engine as such, it happens in strongly turbulent flows at high pressure. But of course understanding that from a theoretical point of view it is very complex, which we will reach there. We will of course go there and develop suitable models for analysis, but then we considered that to understand that first we need to understand the unit building block of such complex flames, and to that end basically we are taking up the analysis of laminar flames. So once again here we will go to this laminar premix flame analysis, similar to what we have done before, but previously we have done it for an adiabatic planar laminar premix flame in a double infinite domain, where you remember we obtained this expression for the burning flux of f naught square, which was proportional to, if you remember, it was proportional to lambda by Cp times Bc Lewis number, this e to the power of minus Arrhenius number divided by Zeldovich square. Okay, so that we have derived, but that was for an adiabatic condition where there was no heat loss. Now what we will do is that we will consider the same premix flame, this planar laminar premix flame in a doubly infinite domain, but here we will consider the effect of heat loss, and we will show that how by considering the effect of heat loss a flame can essentially extinguish. So it is intuitive to understand that if once again we will see that how increasing heat loss can lead to the point of extinction, and by doing a phenomenological analysis we will derive the point of extinction and the burning flux associated with that extinction point. So this is the analysis here. We will consider the premix flame through extinction, the planar laminar premix flame in that doubly infinite domain extinguishing through heat loss. So so here is the analysis. So now as we have seen that the standard flame, as we have seen before, that the standard flame which is the planar laminar premix flame in an adiabatic condition, that being adiabatic does not exhibit any extinction behavior as such. So for finite Yu, that is unbound fuel mass fraction, if it is a lean premix flame, you have a finite F0, which expression I already told you. But now what we have is that instead, this was the adiabatic flame which we initially had. This is the adiabatic flame temperature essentially, this temperature, and now instead of that we have a flame in which there is some heat loss. So, whenever there is a heat loss, of course, the temperature will deviate from that adiabatic flame, and we will estimate the different modes of deviation, how much it will, how much the temperature or how much heat loss can happen through the preheat zone, that is this zone, how much of heat loss can happen through the reaction through the inner reaction zone, and how much of heat loss can happen through the final product zone, and we will sum them up and see how we can obtain an expression for F. But this F naught is not F0, because F0 represents the idealized standard condition where there is no heat loss. So, now we will find out F in terms of F0. Okay. So, that is the idea here. So, F is corresponds to the situation where there is the burning flux under heat loss. Okay. So, this is the situation that we will consider. Okay. So, that is to that end, once again we will proceed with this analysis here, and so what it is intuitive to understand that heat loss, what it does essentially is that heat loss lowers the flame temperature from the adiabatic flame temperature. Okay. And that can essentially leads to a abrupt extinction. Now, why abrupt? Because it is an because as we have seen that the temperature, the burning flux essentially is an Arrhenius dependence on the burn gas temperature. You see that of course, it has a it has a power law dependence on that also. So, if you remember that we obtain that F0 square is essentially T add to the power of 4 times e to the power of minus T activation by T add. Okay. So, it has got both Arrhenius dependence as well as power dependence. So, this Arrhenius dependence is actually very sensitive. So, if you perturb the flame temperature a little bit, your F0 square will be perturbed. Okay. And because this was the for F0, so by that analogy we can expect that the actual F0 will also be something like Tf to the power of 4 times T minus Ta by Tf to the power of T by Tf, whereas this Tf is essentially this Tf. Okay. That is the if the flame is undergoing heat loss, then the burnt or the maximum temperature that it will reach is given by Tf. Okay. Whereas, if there is no heat loss, then the flame temperature, the maximum temperature it will reach is this adiabatic flame temperature. So, we will expect this same analogy, and we will show that this essentially will be true, and so that is the then the question would be that you see that here we have an Arrhenius dependence. Of course, T add is fixed, it does not change, but Tf can vary, that is if you have more and more heat loss, your Tf will continue to decrease, and this will essentially decrease F naught square. So, at some point there will be an abrupt extinction, because this has a very strong Arrhenius dependence. So, we will do this analysis in a phenomenological manner. One can do this analysis in a more detailed Frank-Kamenetsky analysis with heat loss also, but we will not do that. You can take a refer to the CK Law's book to do that to check that analysis. Okay, but you see this is a practical condition, because under no engine, in no engine you have a flame which is adiabatic. Okay, in most you have some heat loss here and there somewhere. So, it is important to understand how a flame behaves under the under a heat loss, and of course, the system becomes non-conservative because you have heat loss. Okay. So, radiation of how, so if you ask that question that how can it have heat loss, well, radiation is of course a very inherent heat loss mechanism which is present in small or biggest extent depending on the type of the flame. Okay. So, now we will see that that we will find out the heat loss in different parts, okay, of the flames. So, we say that this is the heat loss parameter. It is the essentially this LT, this capital LT will represent this the heat loss in the preheat zone with this capital LT. L is the heat loss parameter, T is the temperature. So, L is a function of temperature, and this is essentially a volumetric heat loss rate. So, then the total heat loss, if this is a volumetric heat loss rate, so then the total heat loss flux, that is heat loss per unit area, because of course we have to consider in unit area, then Q minus, that is this region is minus, this region is plus. If we say stick to the previous convention, we will say that this is essentially 0 to LD, that is integrate from, this is the part from 0 to, this is the integration domain. LD is the flame thickness, if you remember, is the heat loss, volumetric heat loss times dx, and that we can say that okay, if we assume that this essentially is constant, this heat loss rate, just for the first cut analysis, we can say that this is LD times L. Now, what is LD? If you remember, LD is essentially lambda by Cp times F, and it can be shown that this LD times F is, whereas is essentially equal to lambda by Cp. where lambda is the thermal conductivity, Cp is the constant pressure specific heat. Okay, now this LD times F, this LD is neither LD0, this F is neither F0. So this LD is essentially the flame thickness when the flame is undergoing heat loss, and F is the burning flux for the flame when it is undergoing heat loss. So this is not equal to F0, this is not equal to LD0. Okay, now you see that why are this the fact that we can expect that the flame will undergo a rapid extinction, can undergo a rapid extinction under some amount of heat loss, can be understood from this analysis itself. How? It can be understood because of the fact that suppose when your heat loss rate increases. Okay, what happens when your heat loss rate increases? When your heat loss rate increases, then of course the total heat loss increases, Q increases, right, Q minus increases. When Q minus increase, what happens? When Q minus increase, of course the temperature will come down, and as we know that the heat flux, the burning flux is essentially a very strong function of temperature. So when heat loss increases and the temperature comes down, then this F, this also will come down. When F comes down, what happens is that because LD times F is equal to lambda by Cp, then LD will increase, that is the flame thickness will increase. Okay. So when the flame thickness increases, now the heat loss happens over a much larger volume, and this will again go and feed back to Q minus. Okay. So you see that there is a nonlinear, there is a kind of a feedback mechanism when there is a little bit of heat loss, it is just not a straight direct. When the heat loss LT increases, it is not a straight direct goes into affect the total heat loss. It of course directly affects the heat loss, but then the feedback mechanism again goes back and to reduce the Q minus further, and that is the reason why you have the rapid extinction when you have some amount of heat loss. Okay, so from that we can expect that if there is an epsilon order of change in temperature, there will be actually an order of 1 change in burning flux. So that is the reason we will see that also. So now it can be shown that your Q plus by considering basically the convective loss, we can also show that will also be essentially lambda by Cp by F times L. Okay, so both in Q minus and Q plus both will be equal to this same expression. Okay. Now we consider that overall energy conservation. Now you suppose the condition that if there was no heat loss, if L was equal to 0, okay, if there was no heat loss, then the system would have been adiabatic, then the overall flame temperature would have reached the adiabatic flame temperature. So we can say that this, if there was no heat loss, that is we can say that this F Cpt add minus Tu is essentially F Cptf minus Tu plus this heat loss rate. So this is the current temperature that has reached, and this is the loss. So by energy conservation, if we add these two, we would have reached the adiabatic flame temperature. Okay. So then we can write that, then we can write Tf essentially is equal to in this form as essentially this T add minus times 1 minus L dash times F tilde square, whereas F tilde is nothing but your F by F0. Okay. And your we can this L prime is nothing but a heat loss, a normalized heat loss parameter, which is essentially given by this thing, and this F tilde is of course equal to F by F0. And now if we just put this thing here, okay, if we will go back into the standard flame result, that is F naught square is equal to lambda by Cp times W naught by Zeldovich number. Okay, and this thing was this W naught equal to e to the power of minus Ea by RT0. Now if we now replace this thing, then we say that if we say that yeah, the similar dependency will hold also when there is some amount of heat loss. So we will see F square is equal to lambda by Cp times W, but not W0 by Zeldovich number, whereas now W is essentially represented by e to the power of minus Ea by R0 times Tf. You see that is the temperature. So we say that the burning flux only responds to is responding to the temperature, because that is the most important factor that controls the burning flux. So we say that essentially the same functional dependence holds, and we only change the temperature. So then we can write essentially this W in terms of these heat loss parameters and these things in a manner that this is essentially is equal to this. Okay, you can just do the analysis. It's not at all complicated. It's quite straightforward. And then whereas this L tilde is essentially equal to L tilde is essentially equal to your this is your quantity here. Okay, so With this you can estimate that we can find out that this normalized burning flux F tilde square will be essentially equal to F tilde square log F tilde square will be essentially is equal to minus L tilde, whereas L tilde is nothing but this quantity e to the e minus E r 0 times L prime, whereas L prime is given by this. So, I will not go into the detailed analysis, you should do it actually on your own, and but this shows that just by considering the burning flux dependence on temperature, we can estimate this heat flux ratio, we can estimate the burning flux ratio, that is this F tilde is essentially F tilde is nothing but F by F 0. We can estimate that ratio, and we can find out the functional dependence, and this is essentially a nonlinear dependence comes, that is F tilde square ln F tilde square is equal to minus L tilde. Okay. So, this is the situation. So, we can, and if we plot now this thing, we see that at, of course, if we plot this whole quantity, that is F tilde as a function of this normalized heat loss parameter L. So, we see that when L is 0, then F tilde is equal to 1. So, which is correct. Now, as you increase L, we see that this F tilde slowly decreases, that is the ratio becomes smaller than 1, smaller than 1, smaller than 1, and then at this point it has a basically has a turning point. So, then this turning point is essentially the extinction point, because it can be shown that the later this branch is essentially unstable. So, the flame essentially is essentially exists up to this point, and that is at a value of this L V tilde is equal to 1 by E. So, at that value this F tilde is essentially given by this thing. So, this clearly shows that this extinction point is given by this thing, and this is that that is when you have a heat loss, when you have increasing heat loss, then extinction happens rather suddenly, because you see here, if you look into this region here, it jumps, it goes initially gradually, and then it suddenly jumps like that before it turns. So, this is the nonlinear behavior that we are talking about, and this corresponds to essentially the extinction. So, this analysis clearly shows that with increasing heat loss, you will get extinction, and you will essentially get heat extinction for all flames, and that is intuitive to understand, but this gives a very beautiful expression, this F square log F squared is equal to minus L, and from that which we can calculate this analytically calculate this extinction point. So, this is an important analysis that we have done. Finally, we will end this topic with this flammability limit. This is the limit at which mixtures can essentially can propagate as a premix flame. Of course, if the system is particularly perfectly adiabatic, which is not a practical scenario, so then it is very difficult to, or rather impossible to find an extinction limit. But if there is some small amount of radiation, then the flame this shows a this Kemkin or this calculations of this one dimensional premix flame with the radiation shows this kind of non-adiabatic behavior, where it has a extinction point, and that is happens, and that we can quantify as the flammability limit, and for that we can show that this extinction happens for methane air mixture. From calculations we see that it happens at 0.493, whereas for empirical it happens at essentially 0.48, and this adiabatic flame temperature at extinction is essentially at 41450 Kelvin, which is quite small with respect to the stoichiometric adiabatic flame temperature. So, with that we come to an end for this part of this limit phenomena, and we essentially come to an end for all our laminar flame analysis, and then we will move on to turbulence and turbulent flame analysis. So, till then, goodbye.